When SE Linux issues show up for the first time, they often feel like a system that is refusing to cooperate for no clear reason. A service that used to start suddenly fails, a process can read some files but not others, or an application reports permission errors even though the normal Linux permissions look correct. For beginners, that combination is frustrating because it feels like the rules changed without warning. The important truth is that security-enhanced Linux, SELINUX, is not random, and it is not designed to break your system. It is a security control that enforces additional access rules beyond the traditional user and group permissions, and when it blocks something, it is usually because the access was not permitted by policy under the current labels. The goal in this episode is to build a calm thinking framework so you can tell the difference between policy, context, and booleans, and so you can respond in a way that restores function without weakening the system unnecessarily. You will learn how to interpret the situation as a mismatch between what a process is allowed to do and how resources are labeled, rather than as a mysterious failure that can only be solved by turning SELINUX off. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A solid mental model starts with recognizing that traditional Linux permissions answer one question, while SELINUX answers a different question. Traditional permissions focus on identities like user, group, and mode bits, and they determine whether an identity can read, write, or execute. SELINUX adds a mandatory access control layer, meaning the system enforces policy rules even if traditional permissions would allow the action. That is why you can see a case where a file is world-readable, yet access is still denied, because SELINUX policy says a process of a particular type is not allowed to read a file labeled with a particular type. Beginners often assume a permission denial must be explained by user and group rules, and when those look correct, they get stuck. The correct next step is to remember that SELINUX is an additional decision point, and it makes decisions based on labels and policy rather than on user and group alone. This model is calming because it turns a confusing denial into a predictable question. What did the policy allow for this process type and this target type? The word policy is central, but it helps to define it in practical terms rather than treating it as a black box. An SELINUX policy is a collection of rules that describe what kinds of processes are allowed to access what kinds of resources and in what ways. The policy is built around types, which are labels that classify subjects and objects. A subject is usually a process, and an object might be a file, a directory, a socket, or another system resource. A rule in the policy might say a process of type A can read files of type B, but cannot write them and cannot create them. This type-based approach is what makes SELINUX powerful, because it applies even when processes run as powerful users. It also means that correctness depends on labeling, because the policy can only enforce the intended rule if the process and the resources have the expected types. For beginners, the key insight is that policy is the rulebook, but the rulebook only makes sense when the labels on the players are correct. If the labels are wrong, the policy will still be enforced, but it will enforce the wrong outcome for your situation. This leads directly to the concept of context, which is the label information SELINUX uses to make decisions. Context can sound abstract, but the simplest way to think of it is as a structured label attached to processes and objects that describes their security identity in SELINUX terms. When people say a file has the wrong context, they mean its label does not match what policy expects for the role it is playing. That mismatch can happen in many normal operational scenarios, such as copying files from one location to another, restoring from backups, extracting archives, or moving content into a directory that has different labeling expectations. A beginner might think that moving a file preserves its meaning, but SELINUX cares about how the file is labeled, and the label might need to change to match its new purpose. If a service expects its configuration file to be labeled a certain way, and the file is labeled differently, the service might be blocked from reading it even if the file permissions are correct. The calm response is to treat labeling as a first-class property, not as an afterthought. A helpful way to organize your thinking is to treat SELINUX failures as falling into three broad buckets. Policy does not allow the action, context is wrong for the resource or process, or a Boolean setting is altering a policy decision. The first bucket is a genuine policy restriction, where the policy was intentionally designed to prevent that interaction because it is risky. The second bucket is a mismatch, where the policy would allow the action if the labels matched, but the labels are not what the policy expects. The third bucket is a policy toggle situation, where the policy includes conditional rules that can be turned on or off through Booleans. The reason this classification helps is that each bucket suggests a different safe response. If the issue is wrong context, the fix is usually to correct labeling, so the intended policy rule applies. If the issue is a Boolean, the fix might be to enable the appropriate behavior in a controlled way rather than rewriting policy. If the issue is a true policy restriction, the fix might require an intentional policy adjustment or a design change in how the service accesses resources. This classification keeps you from using the blunt tool of disabling SELINUX, because disabling treats every bucket as if it were unsolvable. Booleans are often misunderstood by beginners because they sound like a simplistic switch, but in practice they represent deliberate policy design choices. An SELINUX Boolean is a toggle that changes whether certain optional policy rules are active. The reason these toggles exist is that environments differ, and a policy might need to support a safe default while allowing certain behaviors in specific contexts when an administrator decides it is appropriate. For example, a service might sometimes need network access or access to user home directories depending on how it is deployed, and a Boolean can allow that behavior when needed. The important idea is that Booleans do not remove all protection. They enable a specific set of permissions that the policy authors considered as an optional case. This makes Booleans a safer adjustment than arbitrary broad permissions changes, because the change is bounded by the policy's design. Beginners sometimes assume that any change to SELINUX is dangerous or complicated, but Booleans are meant to be a controlled and auditable way to adapt policy to real deployments. Thinking of them as policy-approved options is a good mental frame. The way you avoid panic is by adopting an evidence-based flow that starts with understanding what was denied and why. In SELINUX, denials are not silent mysteries. The system records them, and those records are the key to classification. You are not trying to guess the rule. You are trying to identify the subject type, the object type, and the requested action, and then determine whether the denial is expected or a mismatch. When you see a denial related to a service reading a file, the first COM question is whether the file is in the expected location and labeled for that purpose. When you see a denial about a service making a network connection, the COM question is whether policy considers that connection optional and controlled by a Boolean. When you see a denial that seems to block a behavior that is clearly risky, the COM question is whether the service design should be adjusted to follow least privilege. The point is to treat denials as structured signals rather than as vague complaints. That approach makes SELINUX feel learnable because it turns the problem into a label and rule matching exercise. Context issues are especially common during routine operations, and they produce a very recognizable style of failure. A service might work with files in its default directories, but fail with files placed in a custom directory. This often happens when someone relocates a data directory to a different path without considering labeling expectations. Traditional permissions might be identical, but SELINUX labels differ by directory purpose, so the policy allows access in one place but denies it in another. This is not arbitrary. It is intentional compartmentalization that reduces risk by limiting where a service can read and write. The beginner misunderstanding is to assume that if a path is readable, any service can use it, but SELINUX is designed to prevent that broad access. The proper response is to align the file's labeling with its intended role, not to weaken policy globally. When you develop the habit of thinking about where files live and how they are labeled, you can prevent many SELINUX issues before they happen. That preventive thinking is part of becoming an administrator who designs changes with security layers in mind. Policy restrictions can also appear when you use software in a way that is outside the assumptions of its targeted policy domain. For example, running a service in an unusual way, storing its data in non-standard places, or combining roles on one system can create conflicts with policy expectations. In those cases, the denial may be the policy doing exactly what it was meant to do, which is to block unexpected interactions that could broaden the impact of a compromise. Beginners sometimes treat that as SELINUX being overly strict, but the deeper idea is that security controls encode assumptions, and when you violate those assumptions, controls will push back. The right operational response is to decide whether you should change your deployment to match standard patterns or whether you need to intentionally adjust policy to support a new pattern. Adjusting policy can be valid, but it should be done with a clear understanding of what access you are granting and why. This is where the phrase "how to think, not panic" matters. You are choosing between aligning behavior to policy or extending policy thoughtfully, rather than disabling the control out of frustration. That decision-making discipline is what keeps systems secure while still functional. Another beginner trap is confusing SELINUX denials with ordinary permission problems and then applying ordinary permission fixes that do not address the real cause. You might change ownership, add group access, or make a file world-readable, and nothing changes because SELINUX still denies the interaction. This can lead to a spiral where people keep loosening permissions, creating security risk, and still not fixing the problem. The better approach is to treat traditional permissions and SELINUX as two gates that must both be satisfied. If either gate denies access, the operation fails. When you suspect SELINUX involvement, you avoid making broad permission changes until you understand the denial, because broad changes can create long-term exposure without solving the issue. This is a key operational safety habit. Do not solve an access mystery by opening everything up. Solve it by understanding which gate is blocking and then correcting the specific mismatch. This habit aligns well with Linux Plus goals because it reinforces least privilege thinking rather than shortcut thinking. Booleans deserve one more careful point, because they can create subtle surprises when you move systems between environments. A system might have a Boolean enabled in one environment to support a particular deployment pattern, and then when that system is rebuilt or migrated, the Boolean might be disabled by default in the new environment, causing a service to fail unexpectedly. Beginners might think the service configuration is wrong, but the real difference is policy toggles. This is why governance around security settings matters, even for something that feels like a small switch. When you treat Booleans as part of the system's intended security posture, you are more likely to document them, check them during builds, and avoid surprise breakage. It also reminds you that security controls and operations are inseparable. A service's ability to function depends not only on its configuration, but also on the security policy environment it runs within. When you view Booleans as part of that environment, you can predict when a service might behave differently after changes. As we conclude, the central message is that SELINUX failures are solvable when you approach them as a structured mismatch problem rather than as an obstacle to be removed. Policy is the rulebook that defines allowed interactions based on types, and it is designed to enforce least privilege even when traditional permissions would allow broader access. Context is the labeling that tells the rulebook what kind of process and what kind of resource are involved, and many failures come from context mismatches introduced by normal file moves, restores, or non-standard paths. Booleans are policy-approved toggles that enable optional behaviors in controlled ways, and they often provide a safe way to adapt policy to real deployment needs without rewriting everything. The calm way to think is to classify denials into policy restriction, context mismatch, or Boolean control behavior. Then choose the least risky correction that restores function while preserving security. When you learn to do that, you stop seeing SELINUX as random and start seeing it as a consistent system with meaningful signals, which is exactly the mindset Linux Plus wants you to build for secure and reliable administration.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.